Hello again and welcome back to my review of my solutions for Advent of Code 2024 in ARM assembly for the Game Boy Advance. I completed 10 days this year in ARM assembly and we are on day number 1. So let's have a look at today's problem. So we'll skip most of the story up here. We have two lists of numbers side by side, and it says that we need to pair up the smallest number in the left list with the smallest number in the right list, then the second smallest in the left the second smallest in the right, and so on. So we need to sort the lists with each pair of numbers, one from the left, one from the right. We need to add up all the distances. For example, we have a 3 on the left and a 7 on the right. The distance is 4. So we need to subtract the smaller number from the larger, or we need to do an absolute subtraction. It will show the absolute result, in which case we can subtract either side, and we'll end up with a positive result. So we do find these distances and add them together, right? Add up all the distances and then give a result. That's fine. And then we want to, for part 2, because I'll do part 2 at the same time, right? We need to calculate a similarity score by adding up each number in the left list after multiplying it by the number of times that number appears in the right list. Alright, so for example, this list here, first number is a 3. It appears in the right list 3 times. 1, 2, 3. So 3. So we multiply it by 3. 3 times 9. 3 times 3 is 9. Put it in there. Great. Second number is a 4. It appears in the right list once, so multiply it by 1. Right, and we add those together. 2 does not appear in there, so it's multiplied by 0. 1 does not appear in there, multiplied by 0. We get 3 in there again, so it's another 9. 3 in there again, so it's another 9. Right. So we've got those as well. Okay. So let's have a look at our solution I have here. Let's get rid of the browser. Don't need that anymore. Alright, so what I have here, we'll start with these addresses. Okay, ASCII num. I have this ASCII num here. I know I'm missing an I. That will be a feature all the way through these solutions. And I'm on the internal RAM for the ASCII number. So this is where I read in numbers into memory, ASCII numbers into memory, and then convert them into binary. Then we have this LARP, which is the left array pointer. I'm pointing external RAM, plus 300 is where it starts. And then the RARP, which is the right list. We're starting at external RAM, starting at 4,400. Fairly arbitrary, but nicely placed in the end. So we start on the solve array. We push these registers, save off those registers. We've got our input address start and end. We're using R10 as an offset. We've got this toggle on R4, which is going to be if I'm reading the left number or reading the right number, which determines where we're putting it into memory. And I'm not sure why I've got move 6 here. It starts at 0. We'll find out a little bit later. It signals if we're at the end of the input. So if we reach the end of the input, we might have to still convert an ASCII number, right? We might still have to convert an ASCII number. So hitting the end of the input, I can't just exit immediately. We still might have to go through the process of converting a number and then go into the rest of the program. Alright, so what do I do here? I move R8, the R8 thing there, into R0, then I add R10 to it, which is an offset, and then I compare R0 to R9, which is the end of the input. And if we're at the end of the input, if it's equal, then we're at the end of the input. Either way, which is where I'll signal that R6. Either way, we go to convert ASCII, we branch to convert ASCII. Oh no, this is a branch EQ, right? So if we are at the end of the input, we'll branch to convert ASCII. Otherwise, we'll load 1 byte, right? Load register byte into R1 from the address R0. This is going to change, and I do this a number of different ways, actually, going through these solutions. This time here, I'm like putting R8 and R10 together, the offset together, to make R0. Oh, that changes. So we load that byte, we compare it to hex 20. Hex 20 is a space. These, not in this demo here, but you'll really see it. Oh no, wait. I think it is actually 2 or 3 spots. Let's have a look. Can I actually see my browser? Let's have a look at what we actually get in my puzzle input. So you can see here on the actual puzzle input, there's 3 spaces between numbers. They're actually all 5-digit numbers got through here, which is fine. So that comes into this as well. Get rid of the browser. You'll see when I have this branch, this compare, I then do an add EQ. So I add 2 to the offset if the byte value is 20. And then I branch to convert ASCII. And also if it is OA, which signals a new line, we branch to convert ASCII. Right? If none of those have branched out, then I'm loading a digit. Right? Then I've loaded a digit from my input. And so we'll convert this. We AND it with 000F, which will give us the binary encoded decimal version of the ASCII number. We load ASCII num, the value from ASCII num R3, which is going to be the offset value. Right, and then I load that address first. Then I load the byte. I load a byte from that address. Offset, which is probably going to be, it will start off at 0. Then I add 1 to it. Then I store it, R1, which is our binary encoded decimal, into ASCII num address with the offset in R2. So the first time it will be with an offset of 1, and then I store the offset into the ASCII num address. Right. So effectively, the offset is the number of values in ASCII num. I do it. I don't know. I like it. I've come to like doing it this way, because I can start with the offset and just count down, like count from the right side down, and then when it hits 0, I've reached the end of the actual numbers in the list. I kind of like it. And then I fall into inc offset, which adds 1 to R10, and it branches back to read loop. So the next part is this convert ASCII, right? So let's have a look. We want to, I don't know how you actually do that. That's Control D, isn't it? Oh, no, I can't remember. Wait a second. I don't know. Anyway, trying to remember my shortcuts and things and any of them. Anyway, so convert ASCII. We're going to move 0 into R1. Going to move R11 to 1, R7 to 10, and then we load our address, our pointer, our offset really. We load our ASCII num address, and we load our deleting lines again. Then we load our offset into R2. So how many values are in ASCII num? And we go into the loop convert. So the first thing we do, we load a byte. We load the first value, which is the last value, right? The ones column from ASCII num. We multiply that by the value in 11, which is going to be 1. Then we add it, and we delete the line again. We add it to the value that's in R1, which starts off at 0. And then we multiply R11 by R7. And the thing about the multiply value here is that while here with add, the first, right, this is the destination register, and these are the two source registers. So we add R1 to R0, or R0 to R1, and we store the result in R0. With multiply, you can't have the destination as the same register as the input source ones. So I have to put it into something else, like R0. So we multiply 11, deleting things again. Sorry. We multiply register 11, which starts out at 1, right up here, by R7, which is 10. We store it into R0, and then we move it back into R11. So for the next step in the loop, it's going to be 10. R11 will be 10. Subtract 1 from R2, which is our, that offset from our input. We branch back if it's not equal. So if it's not equal to 0, we branch back up to here, and we do the next digit, which will be the tens column, which will multiply by 10, right? And then we multiply that 10 by 10, make it 100. The next digit will be the hundreds column, and the thousands columns, the tens thousandths column. We're all adding that together into R1. So once we are at the end here, once we've finished this loop, we have a look at, we delete that line again. We have a look at R4 if it's, and this is one of these things again in ARM assembly, where we can put these comparators on basically anything we want. So compare R4 to 0. If R4 is 0, we want to change R4 to a 1. So the next number will be, the next time we go through this, convert ASCII, the next number will go into the other array. And then we load into R3 the address of the left array. If it's not equal to 0, then we put 0 into R4, and we load R3 with the address of the right array. So this is something nice you can do in ARM that you can't do in like 6502. 6502 you'd have to do that comparator, and then depending on, right, you do a branch EQ and a branch not EQ, and just branch to different subroutines, and then from there branch back into the rest of the code, sort of thing. But in here I can just do it like this. So then I load R2, which is again R2 is from this address here. is going to be the offset, the number of values that are in the array. And now I have to add 4. Now because we get fairly big values, I'm using 32-bit values in these arrays. So instead of adding 1 to the offset, I have to add 4 to the offset, 4 bytes to the offset. Right? So I add 4 to it, to the offset, we store it. Deleting things, we store it in the array with that offset, and then we store the new offset at the array pointer. And then we clear ASCII num. We clear the ASCII num offset. We don't actually clear the whole list because we don't need to. And then I compare. I check if what the value of R6. If it's a 1, then we branch to sort lists. If it's not 1, we branch to inc offset. We branch to inc offset. We're still going through the rest of the input. So finish the input. We need to now sort the 2 arrays. We've got these 2 big arrays in memory. So I have to run our sorts. So I do sorts in serial. First we load R9, register 9 with the left array, and R8 is the length of the array, or well, the offset of the last value in the array, and I subtract 4 from it before we go into run sort. Not sure why exactly. Who cares? And then we run it, branch it to run sort. So let's have a look at the run sort, shall we? Here we go, down here. Relatively short. So I load. So I mean, I'm loading this again, basically. Whatever. Load R6 with that offset from R9. Load R0 with R8 with that R8 offset, the one with minus 1 from the offset. So 0 is now the second to last value in the array, and R6 is the sort of the address of the last value in the array. Yeah, the address of the last value in the array. And then we branch to subsort. And then we go through subsort, branch into subsort here. And we go into the sort loop. So we load into R1, I'm deleting things again, that value, basically the very last value in the array, and we compare it with R0. Now, if it's greater than let's see, I think yeah, so if R1 is greater than R0, then I store R1 in the position of R0, right? And I store R0 in the position that R1 was at. So what I'm effectively doing is a bubble sort, right? I'm bubble sorting it. So it's effectively pushing the larger values as far towards the beginning of the array as possible. That seems a little bit odd because the way they have it in this list is to do, and the sort of problem is to do the lowest values first, but seeing I'm reading these arrays, I'm generally reading these arrays backwards. I'm moving the larger values to the front and the small values to the back. That's fine. It works, right? So we swap them around if R1 is greater than R0, and then I move the value of R1 to R0, right? Let's just swap them around. Subtract R6, subtract 4 from R6, so that following pointer, I deleted again. Subtract 4 from it, so move it back one place, and we compare it to R8. If they're now the same, they're in the same position, then we end this sort loop, right? The subsort. And so we come back out of the subsort, we subtract why am I doing this? I should really just have this gone and have that there. Anyway, whatever. Anyway, so I'll subtract 4 from R8, right? So the first time through, it was in the second to last position, and the follower started in the last position. Subtract 4 from it, so now it'll be in the third to last position. The second time through will be the third to last position. We go back to start the loop again, so R6, the follower, will start in the first position, right? And then we'll go into the loop again, right? So it will compare the last position to the third to last position. If it's larger than it, they'll swap them around, and then it'll go effectively the third to last position to the second to last position, and if it's the second to last position is larger than it, it'll swap them around, and in that way it's shuffling them all around and sorting the arrays, right? So it'll do that for the left side, and when it's finished, it'll do that for the right side, the right array as well, and then we are ready to solve the two, part 1 and part 2. So we start with part 1. R6 is the result. We're loading R6 there, and it looks like I'm clearing it, even though it should already be cleared. Fine, whatever. It's fine. So, and then I load my two arrays into R8 and R9, and then an offset thing for R10, and then we load R5. Actually, it looks like I might be going through from left to right. so I think I sorted them from largest to smallest, but then I'm actually going through it from largest to smallest instead of smallest to largest. But I mean, it doesn't matter. In the end, it doesn't matter, because you just need the sorted lists. Who cares? It's fine. Alright. And then, but I'm also loading the value of R5, which will be the number of times effectively I have to go through the list. So, part 1 loop. I've just deleted the things again. We load the values from the each list, right? Both are the same offset, and we compare. So I compare the two values, right? And what I'm doing here is that I'm doing a subtract. So if the left side is less than the right side, then I subtract the left side from the right side and still the result in R2. If the right side, well, if the left side is greater than the right side, then I subtract the right side from the left side and put the result in R2. Again, a nice feature of ARM. I just do this compare, and it will like skip the irrelevant one, right? It'll just skip the one that's not relevant. I think, yeah, I've got less than for this one here, and then greater than or equal, right? Doesn't matter. If it's equal, you could do less than or equal and greater than, or less than or greater than and greater than equal. Doesn't matter, right? Then I load R4 into R4 the value from R6, which is our result, right? Our result pointer from up here, and I add R2 to the result, that difference to the result, and we store it back in there, and we branch. And now we branch to part 2. This is because I'm doing them both at the same time. It's fine, right? We'll skip over that for a second. We'll just finish off this one. So we add another 4 steps to the offset, and I compare that to R5, which is the entire length. And if it's less than that, right? Less than or equal, LE, less than or equal, we branch back to part 1 loop, right? So this goes through a loop until we get to the end there. Part 2, right? We load in because we've backed up those registers. We're safe to load in R6 register result 2 and our offset again, right? Another offset. R4 is now 0. I subtract 4 from this again, from the entire list for some reason, whatever it is. And then I'm going to loop. I have to count how many occurrences of the value in R0. Remember, R0 from loop 1 was the left-hand side. Occur in thing. And so effectively, like, because it's multiplying by the number of occurrences, you can just add the value if it's the same, right? It's the same thing. So we've got this part, ding dong. We've got this part 2 loop here. There is a multiply in here. Or am I? Oh no, wait. No, I'm not doing that. I could have done it, but I'm not doing that. Instead, I'm just adding 1 to R4 each time. So I should have done that, just added the value each time, and it would have been the same. It would have been the same result. Oh well, whatever. Probably would be faster in the end. So instead, what I'm doing is that I am adding up occurrences. So right, we load the value into R1. I'm not sure if that's actually correct, but I get the correct result, so it's kind of weird. Oh well. It works. We'll just say it's fine. So load value into R1. We compare it to what's in R0. If it's the same, then we add 1 to R4, subtract 4 from the offset we're doing on our loop, and we branch so long as it's greater than 0. Right? And then once we get to the end, I delete those lines again. Once we get to the end, we multiply R4 by what the value that's in R0. So multiply the occurrences by the value into R2, and then we load R3, the value that's in result 2, and we add R2 to R3, and we store R3 back in R6, and the value for part 2, result 2. And then we go back and we do the next stage of the list, right? So once we've finished doing part 1 loop, we will have finished doing part 2. We hit finish day, and that's the end. We go back to waiting for input. So that is day 1's code completed. Let's see it running. Alright, so we've got our emulator here. It's ready to run. And I just need to push the button. And right now it's reading the numbers and sorting the lists. But you can't see that. And here we go. Result. Okay, you get the correct result because of course we do. Let's have a look at that again using the memory. I think I got this one here. Boom. Yes, we've got it up. Okay. So right now, looking at our memory, I have the external workram visible. Let's have a look at the internal workram. See, we've got our result here. Number 1 and number 2 in binary, and in the binary encoded decimal 3574690, and the other one down here. You can see that it's constantly updating. This was an early day. It was updating every frame, which slowed down the result a little bit. In the external workram, you can see the numbers in here. We have, first off, this is the number of values in our result. Let's see, because it's FA0, 4,000. 4,000 values in the results. And we're up here with like... This might actually be the lowest ones. Okay. No, it does look like I've got it sorted the other way around. Yep. I think I was confused about the way I was sorting. I think the highest values are last and the lowest values are next. So let's see, where are we? Finding the, there we are, there's the split between the two lists. And yet there's the largest number, 34,449. No, that's not right. 99,985. That'd be right. Okay, and you got the second list starting here and going on. Alright, so let's have a look one more time, shall we? We'll have a look at this view. So let's start this up. And you can see nothing happening, and oh, here we go, sorting the numbers. And it's sorting the other list now. Oh, and now it's running. And we're done. Okay, so that was the first day. Wasn't very difficult. The most difficult thing was writing a sort algorithm on the first day. I was not expecting it. But in the end, relatively short. I think, like, compared to 6502, relatively straightforward. Only, what is it? Like 120 lines or something. We start here at like, what was it? 394 and 260. Okay, so about 170, 180 lines. Not too bad. Okay. Well, hope you enjoyed that. We'll be back again with day number 2 sometime shortly. I hope you'll be back for that, and we'll see you then.